Okay, let us continue with the volume percentage. The second one is volume percentage. It is written by V by V, volume by volume. In the volume percentage, volume by volume, that is the symbol used. And what's the volume percentage of a solution? Say volume percentage is equal to volume of the component, by volume of the solution, We are using the volumes into 100, and that is the equation used for the volume percentage. You take say 100 volume, 100 ml, for example, of the solution. And what will be the volume of each component in 100 ml of solution? That is the volume percentage. So volume percentage is equal to volume of the component by volume of the solution into 100. Instead of the mass, here we make use of the volumes of the components. See, for example, you take 35% volume by volume of, say, ethylene glycol, 35% volume by volume of ethylene glycol, glycol in water. Ethylene glycol in water. You take this solution. Say, what is the meaning of this? Here, the solute is ethylene glycol and the solvent is water. The percentage of ethylene glycol is 35% volume by volume. That means, say, if you take say 35 ml of ethylene glycol plus then 65 ml of water, and that is the mixture, that is the solution. In the total volume 100 ml, there will be 35 ml of ethylene glycol and 65 ml of water. That mixture will be there. And the volume percentage is usually used to express the concentrations of solutions of two liquids. That means the solute is a liquid. So for example, ethylene glycol, and the solvent is also a liquid. Both are liquids. So the volume percentage term is very commonly used to express the concentrations of solutions of liquids. And the equation for volume percentage is equal to volume of the component by volume of the solution into 100. Volume of the solution. For example, 35% volume by volume of ethylene glycol in water. It contains 35 ml ethylene glycol and 65 ml of water in the mixture. That is the proportion. So the ratio will be, the percentage will be 35 by 100 into 100, then 65 by 100 into 100. So 35% volume by volume of ethylene glycol. And this mixture has an importance. See, this mixture is used as an antifreeze. This is used as antifreeze. That is used as antifreeze. And what is the function of an antifreeze? You know, in the motor cars, there is a thing called a radiator. You know that? Radiator. In the radiator, we make use of a coolant. Usually water is taken as the coolant. Usually water, very commonly water is taken as the coolant. That is to avoid overheating of the engine. To avoid the overheating of engine, there is a device that is called the radiator. In the motor car radiator, we make it as a coolant. If water is taken as the coolant, say during winter season, there is a problem. Say at the high ranges, say water, there will be the atmospheric temperature will be sub-zero. Atmospheric temperature will be sub-zero. Minus, the value will be, temperature will be minus, sub-zero. Say -2, -10, like that. And under that conditions, what will happen to water taken in the radiator? You know, water freezes at 0 degrees Celsius. And if the temperature, atmospheric temperature is less than 0, if it is a sub-zero, under that condition, so water coolant taken in the radiator, it freezes. And there is a chance for cracking of the radiator. So we take a mixture that is known as antifreeze. Antifreeze. If antifreeze is used, the freezing of the coolant can be avoided to a certain limit. If this mixture is taken, ethylene glycol plus water mixture is taken in the radiator, say the temperature, the freezing point of the mixture can be lowered to -17.6 degrees Celsius. Minus 17.6 degrees Celsius. So up to this, the mixture taken inside the radiator will not freeze. So the role of antifreeze is to avoid the freezing of the coolant taken. A mixture of ethylene glycol and water, 35% ethylene glycol plus water, a percentage is volume by volume. It is taken as an antifreeze. And the volume percentage is commonly used to express the concentrations of solutions of liquids. Solutions of liquids, both the solute and solvent, both are liquids. Now you come to the third one, that is mass by volume percentage. Third one, mass by volume. Mass by volume percentage. So it is expressed as W by V, mass by volume percentage. This unit is used in pharmacy as well as say the medicinal products. You know, the cough syrup taken. You just examine what is printed on the cough syrup bottle. There you can see the volume percentage of the various components. Similarly, the mass by volume percentage also can be seen. So this unit is used to express the concentrations of the medicinal preparations. So for the pharmacy purposes, pharmaceutical products, the volume, the concentration is expressed in mass by volume percentage. It is the use of it. Now, let us go to the next one, and it is the fourth one. The fourth one is, okay, do you remember, have you written? The fourth one, parts per million. Parts per million. Parts per million. Parts per million. ppm. This unit is used to express the concentrations of extremely dilute solutions. If the amount of the solute is very small, the solution contains only trace amounts of the solute. The solution contains only trace amount of solute. There is only very small, extremely small amount of the solute. In that case, we make use of the unit ppm, parts per million. And what is parts per million? ppm. Say ppm is equal to, say, number of parts of the solute. Number of parts of the solute. Number of parts by mass. Number of parts of solute. Number of parts of solute by number of parts of a solution. Number of parts of a solution. Parts of a solution. Then into million, 10 raised to 6. 10 raised to 6. Million is 10 raised to 6. Instead of percentage. Do you remember? Previously we were taking percentage into 100. 10 raised to 3. Sorry, 10 raised to 2. 100. Only 10 raised to 2. But here we make use of say 10 raised to 6. That is million. So parts per million means number of parts of the solute in million parts of the solution. Number of parts of the solute in million parts of the solution. So ppm is equal to number of parts of solute by number of parts of solution into 10 raised to 6. Here I say only number of parts. The meaning is this: if you express the mass of the solute in grams, then mass of the solution also must be in gram. You have to make use of the same unit. That's all. If the mass of the solute is in kilogram, then mass of the solution, here we make use of the masses. We make use of the masses. Mass of the solution as well as mass of the component. But the units should be the same. If a solute is in gram, solution also in gram. Solute is in kilogram, solution is also in kilogram. Okay. So this unit, parts per million, ppm, is used to express the concentrations of extremely dilute solutions. That means there will be only trace amounts, very, very small amounts of the solute in the solution. Say, for example, the amount concentration of dissolved oxygen. What is meant by dissolved oxygen? That is the amount of oxygen dissolved, O2 dissolved, amount of oxygen dissolved in a given sample of water. So, for example, sea water or say well water, river water. So, in a given sample of water, for example, sea water, say the amount of oxygen dissolved is very, very small amount, only 5.8 ppm. The amount of oxygen is only 5.8 ppm. Or say less than 6 ppm only the amount of oxygen dissolved in sea water. Usually, the amount of oxygen dissolved should be, say, greater than 6 ppm, and that is more suitable for the aquatic living beings. For the the safety of the aquatic living beings, the ppm, number of parts of oxygen dissolved in water, it is 6 or more than that. So, say the dissolved oxygen or the amount of chlorine in bleaching powder, you have written that. I have written that the project. Say the amount of chlorine in bleaching powder, amount of chlorine in the town supply or panchayat supply of water, then the value is expressed in ppm. Similarly, the pollutants in water and in air. Water in and air, water pollutants and air pollutants. There are only small amounts, trace amounts, and the pollutants can be expressed in terms of ppm. These are the applications. So the term ppm, parts per million, is used if the amount of the solute is extremely small value. For example, the amount of dissolved oxygen in a water sample. For example, see water sample, it comes only 5.8 ppm. Similarly, the amount of the pollutants present in air as well as water, that is also expressed in terms of ppm, parts per million. And this is for the concentrations of extremely dilute solutions. Okay. Now let us see some more common terms used to express the concentrations. So the fifth one, that is mole fraction. Mole fraction. Mole fraction of a solution. Mole fraction. Concentration of a solution can be expressed in a term called, a unit called mole fraction. Mole fraction is expressed using the letter X. X is used. And what is mole fraction? What is meant by mole fraction? It is the number of moles of this component in total number of moles of the component by total number of moles of the component. So it will be the number of moles of the component in 1 mole if the total number of moles of the solute and solvent is equal to 1. So we can write it like this. The mole fraction X is equal to number of moles of the component, solute or solvent, whatever it is. Number of moles of the component by total number of moles of all the components. That means if a binary solution, both solute and solvent, and this ratio is called the mole fraction. We are dividing the number of moles of the component by the total number of moles of all the components. So it gives us the number of moles of the component if the total number of moles is equal to 1. Division by total number of moles. Division by total number of moles. That will give you the number of moles if the total number of moles is equal to 1. That is equal to 1. So mole fraction X is equal to number of moles of the component by total number of moles of all the components present in the solution. Say for example, you take a binary solution. You have to see only binary solutions. Say solute, number of moles of the solute, that is equal to solute, that is equal to NB. Suppose it is equal to NB. Then number of moles of solvent, moles of a solute, then moles of a solvent is equal to Na. A is the solvent and B is the solute. Remember, in all my say talk, A represents always, A represents solvent, B represents solute, or N1 represents solvent, N2 represents solute. Here, let me take the solvent and the solute as solvent A and the solute B. Solute to B. Okay. Number of moles of solute is equal to NB. Number of moles of solvent is equal to Na. Then what will be the mole fraction of the solute? That is XB. You call it as XB. Mole fraction of solute XB is equal to number of moles of the solute NB by total number of moles Na plus NB. Na plus NB. That is the mole fraction of the solute. Similarly, mole fraction of the solvent XA is equal to number of moles of the solvent, that is equal to Na by total number of moles Na plus NB, and that is the mole fraction of the solvent. It is seen that XA plus xb is equal to 1. Always the sum of the mole fractions of all the components is equal to 1. So xa plus xb is equal to 1. So if the mole fraction of any one of the components is available, we can very easily calculate the mole fraction of the other components. Say mole fraction of one component is equal to xb. Then what will be the mole fraction of the other component xa? Xa is equal to 1 minus xb, or xb is equal to 1 minus xa. So if the mole fraction of any one component is available, then 1 minus mole fraction of the given component, that will give you the mole fraction of the other component, because xa plus xb is equal to 1. Therefore, xa is equal to 1 minus xb, and xb is equal to 1 minus xa. In general, xa plus xb is equal to 1. Now you come back to the mole fraction. Mole fraction x is equal to number of moles of the components by total number of moles of all the components in the solution. For example, solute is equal to number of moles of solute is equal to NB, number of moles of solvent is equal to Na. So total number of moles of solute and solvent, that is equal to Na plus Nb. Therefore, mole fraction of solute xb is equal to Nb by Na plus Nb. Similarly, mole fraction of xa is equal to Na by Na plus Nb, and xa plus xb is equal to 1. From that relation, if a mole fraction of one component is available, the mole fraction of the other component can be easily obtained by taking the difference between one and mole fraction of the given component. That means xa is equal to 1 minus xb. Similarly, xb is equal to 1 minus xa. Okay. Now, another question arises here. How will you get the number of moles? How can you calculate the number of moles? Number of moles is equal to mass in gram. Mass in gram. Mass of the component in gram by molar mass. Molar mass. That is the ratio. So if mass is available by taking the ratio between the mass in gram. Remember, mass should be in gram. So mass in gram by molar mass, that will give us the number of moles. So number of moles is equal to mass of the substance in gram by molar mass of the substance. So you must remember this equation also for solving the problems. For calculating problems, we need the mole equation also. So come to the mole fraction again. Achyut, what is the relation for mole fraction? How will you get the mole fraction? Mole fraction x is equal to, come on. You complete? Achyut, I am asking you. Diya?
Number of moles of the component divided by
total number of moles of all the components. We have Na moles of solvent and Nb moles of solute. Then what will be Xa? Diya. Xa is equal to
Na by
Na plus Nb. Similarly, Xb is equal to Nb by Na plus Nb. Xa plus xb is equal to 1 always. How can you calculate the number of moles? The number of moles can be calculated, Srihari. How will you get to the number?
Mass in grams by molar mass.
Mass in gram. The unit should be very careful. Mass in gram by molar mass. Say in physical chemistry experiments, from all the chapters there will be problems. For the examination, numericals will be there, problems will be there. No doubt in that. So we can calculate the number of moles using that equation. Say for example, let us solve one problem, and by that we can finish today's workout. Say the problem is this. You please take down the problem. Please take down the problem. Come on. The problem is this. You can write. Calculate the mole fraction of, right? All of you. Calculate the mole fraction of ethylene glycol. Ethylene glycol, GLYCOL. Ethylene glycol, the molecular formula is C2H6O2. C2H6O2. That is the molecular formula of ethylene glycol. Calculate the mole fraction of ethylene glycol, C2H6O2, in a solution containing 20% C2H6O2 by mass. C2H6O2 by mass. Containing mole fraction of ethylene glycol in a solution containing 20% of C2H2O2 by mass. So we have to calculate the mole fraction. Suppose the solution is in water. Solution is in water. Okay. Now, we have a mixture of ethylene glycol and water. 20% ethylene glycol solution in water. What is the meaning of that? In 100 gram of the solution, Manuel, 100 gram of the solution, 20 gram ethylene glycol by mass. It is given by mass. That is the mass percentage. So 20 gram, suppose 20 gram C2H6O2 plus what will be the mass of water, Emmanuel?
80, sir.
Yes, it is 80, correct. 80 gram H2. 80 gram H2. That is the mixture. Okay, written 20 gram C2H6O2 plus 80 gram H2. Out of 100 gram, 20 gram ethylene glycol and 80 gram water. Okay. So we have got the mass now. We have to calculate what? We have to calculate the mole fraction. To calculate the mole fraction, we need a number of moles. But number of moles, that is not given. So what do you have to do? You have to convert this mass into number of moles. So you find out. So moles of C2H6O2 is equal to mass in gram by molar mass. Mass in gram by molar mass. What is the mass? 20 by molar mass. Molar mass is C2H6O2. You find out that. See, this is the margin. C2H6O2. You write fast. Atomic mass of carbon is equal to atomic mass 12. 2 carbon into 2 is equal to 24. Hydrogen, atomic mass is equal to 1. 6 hydrogen into 6 is equal to 6. Then oxygen, atomic mass of oxygen 16 into 2, that is equal to 32. You add this. That will give us the molecular mass of ethylene glycol. What is the value you got? Got it? Come on, come on. Add fast.
62.
That's equal to 62. That is equal to 62. So you 20 by 62. And this is equal to the number of moles of C2H6. We cannot use the calculator. We cannot use the calculator. You can use the logarithm table, or you can directly simplify. Okay, here I shall help you on simplification. What is the rough value you get? Just a one digit. At least one digit. Get it fast. Come on. At least one digit. 0 point. There.
3.
3. You got 3. Got it?
3, 2.
Yeah. So it is a 0.32. That is the value. Similarly, you find out moles of number of moles of H2O water. That's equal to mass in gram 18 by molecular mass of water H2O. Do you remember? Okay. Hydrogen 1 into 2 plus oxygen 16 into 1. And that is equal to 18. Molecular mass of water is equal to 18. Alright? That is equal to 18. So you just study it by heart. Molecular mass of water is equal to 18 U or 18 gram per mole. So by 80 by 18, and that's equal to the value is
4.4.
it is 4.4, correct. 4.4. Now you find out the mole fraction of ethylene glycol. Therefore, mole fraction X of ethylene glycol. Ethylene glycol is usually known as glycol. Is equal to, how will you get it? NB by, this is NB, suppose. And this is Na, solvent. So NB by Na plus NB, that is equal to NB 0.32 by 0.32 plus 4.4 or 4.4 plus 0.32. Now you simplify this. On simplification, the mole fraction of glycol is equal to 0.068. 0.068. That is a mole fraction of glycol. That is the question asked. Suppose you are asked to find out the mole fraction of water also. It is not asked. If it is asked, therefore, mole fraction of H2O is equal to, you can find it by dividing 4.4 by 4.4 plus 0.32. That is a method. But there is a simple method. What is the simple method? XA plus XB is equal to, come on, 1. XA plus XC is equal to 1. Therefore, this is XA, suppose. 1 minus mole fraction of glycol, 0.068. That is equal to, you simplify that, 0.932. The value is a 0.932. You must check it. You must check it. You do it yourself and you must check it. So 0.9332. Mole fraction of, that is not asked. We can calculate mole fraction of water in 2 ways. How? Mass of water by sorry, number of moles of water by total number of moles. That means 4.4 by 4.4 plus 3.32. That is a method. But a simple method is this. We have only two components. In a two-component system, XA plus XB is equal to 1. Therefore, XA is equal to 1 minus XB. So 1 minus 0.068 is equal to 0.932. That's the mole fraction of water. Okay. So this is the method. So remember, in this, only the mass is given. Mass of ethylene glycol and mass of water. Only the masses are given. Number of moles, that's not given. So you have to calculate number of moles. To calculate number of moles, you have to take the ratio between mass of the component in gram and molar mass of the component. For example, here, mass of glycol by molar mass of glycol. How you can find out the molar mass? You simply add the atomic masses. Simply add the respective atomic masses. So you must know the atomic masses, common atomic masses. Hydrogen 1, oxygen 16, carbon 12, sulfur 32. Such a common nitrogen is equal to 14. So such values, common values, you must remember. Then only we can solve the problems. Okay. So that's about the mole fraction of the solute. Next, we have to see molarity and molality. Molarity and molality that we can see the next day, because if I begin with molarity, it will take time. I cannot finish it. So I am not taking it now. I think